This video will be about scientific notation. Scientific notation is used for very, very large numbers or very, very small numbers. I'm going to start with something a bit smaller than 21 million, just so it's easier to see where scientific notation comes from. So if we'd have the number 200, I could write that as 2 times 100. 2 times 100 would give us 200. 100 is a perfect square. 100 can be written as 10 times 10. And then 10 times 10 is 10 squared. Often with scientific notation, they use the older school multiplication symbol, the x. So 2 times 10 squared. Well, starting from the beginning, instead of having to go through this whole process, if we identify where the decimal starts at, decimal starts here, and where we want the decimal to end up. In scientific notation, the decimal must end up always right after the first non-zero digit. So we want the decimal to end up right after the 2. And we just count how many spaces that takes. 1 space, 2 spaces. That's where we get that exponent. So we can really skip that whole process and just count. So when we count to the left, our exponent goes up. 1 space, we add 1 more space, so 2 total. So if we do the 21,456,835, we want the decimal to be right after the 2, 2.1. The decimal originally starts at the end of a number if it's not already written in. So we start here, we want to end here. Often with scientific notation, we don't write out the entire thing, we approximate. So I'm going to approximate right after the decimal. So I'm going to take that 1, there's a 4 next to it, so we leave it a 1. So 2.1 times 10. And then we figure out, well, what's my exponent going to be? So we just count to do that. We have 1, 2, 3, 4, 5, 6, 7 spaces. So 2.1 times 10 to the 7th. Now for a very, very small number, the concept is the same. This time the decimal is already written in, we know where it starts. We still want it to end right after that first non-zero digit. I'm going to round again. Look at the 5 next to it is a 6, so this would round up to be 2.6 times. And now since we're moving to the right as we count, each time we move to the right, we're getting 1 unit smaller. So -1, -2, -3, 4, 5, 6, 7, 8 spaces. So times 10 to the -8. So moving to the right, it's like we're subtracting 1 every time. And moving to the left, it's like we're adding 1 every time. So we can ask some questions about scientific notation. A white blood cell count is normally around 6.5 times 10 to the 9th white blood cells per liter. What is the number in standard notation? So 6.5 times 10 to the 9th. So when we had our very, very large number, our 21 million, that was our approximation of it, we had to count to the left to get it into scientific notation. Well, to get it out of scientific notation, we just count to the right instead. So we originally start with 6.5, we're going to count 9 spaces to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now notice most of those spaces are not filled. If they're not already filled, we just replace those with zeros. So since we counted over, that decimal is actually moving, so we don't have a decimal there anymore. It's 6, 5, 0, 0, 0, 0, 0, 0, 2 more, 0, 0. We can put in our commas. 3, every 3, we put a comma. So this would be 6,500,000,000. Another scientific notation question. Distance from the Earth to the Moon is approximately 2.4 times 10 to the 5th. The distance from Earth to Mars is approximately 142 times greater than the distance from Earth to the Moon. What is the approximate distance from Earth to Mars? So if it's 142 times greater, times is a word for multiply. So it's asking us to multiply these two numbers together. When we multiply them together, we're actually going to multiply only the 2.4 times the 142. The times 10 to the fifth is just going to come down. So 2.4 times 142 is 340.8. Now we run into a problem. This is no longer in scientific notation. We need that decimal to be directly after the 3. So we're going to have to move it 2 spaces to the left to get it directly after the 3. If we do that, that is going to affect the exponent. So on our first page we talked about, well, moving to the left is like adding 1 for each space moved. Well, we've moved 2 spaces, so we're adding 2 to the exponent, and it becomes 3.408 times 10 to the 7th. Now maybe they want you to round at 3.4. You could round it as 3.4 times 10 to the 7th. If they ask for the nearest tenth here, right after the 3, maybe they want 3.41 times 10 to the 7th, or they may just have it written as the entire decimal here. Another form of problem will be to order numbers that some are in scientific notation already, some are not. We want to put them from smallest to largest. So with our negative exponents, the bigger the number here, the 5, is actually a smaller number overall. That would be more zeros in front of the 2, so negative 5 here is definitely smaller than negative 4 as our exponents. That can help us differentiate these numbers. These ones are not in scientific notation yet though, so we need to write them in scientific notation before we can compare all 4 of the numbers. So 0.000389, we want the decimal to end up right after the 3, which is 4 spaces to the right. 3.89 times 10 to the negative 4. Then we do the same thing with the 0.0025, 0.000025. That was 5 spaces. So this is 2.5 times 10 to the negative 5th. So we know the numbers with the negative 5 exponents will be smaller. And then between the two, 2.5 is smaller than 2.76. So 2.5 times 10 to the negative 5th, sorry about that, times 10 to the negative 5th is the smallest number. Next comes 2.7 times 10 to the negative 5th. Then we compare the ones with the negative 4 exponents. 3.1 is smaller than 3.89, so 3.1 times 10 to the negative 4th, and then 3.89 times 10 to the negative 4th. So one last type of problem. The United States generates about 2.5 times 10 to the 8th tons of trash a year. If 8.7 times 10 to the 7th tons are recyclable, how much trash is not recyclable? So what we need to do is subtract these two numbers. We have a total amount, and we have a part that we don't want. We want to know how much is not recyclable, so we don't want this recyclable amount. So we want to do 2.54 times 10 to the 8th minus 8.7 times 10 to the 7th. Now with multiplication, it doesn't matter what the exponents are, but with subtraction, it does. These exponents have to match before we can actually do any sort of subtraction. It's always better to get to the exponents to match to the bigger number. So we want to change this 8.7 times 10 to the 7th. We want to change this to an 8. So basically we want to add 1 to that exponent, which meant a movement to the left. This would be 0.87. Now when we subtract, the 10 to the 8th will just stay there. And we're really going to do 2.5 minus 0.87. That gives 1.63. So 1.63 times 10 to the 8th. Remember again, that's a very, very large number. So those are all the types of problems you'll see for scientific notation. That concludes our discussion of scientific notation.